All of these classes are valuable, but some of them are just more valuable than others if you want to become an embedded or firmware engineer. So let's dive right into ranking them. The first one is Microcontrollers 1. In Microcontrollers 1, you'll be programming in C, bare metal, on an Atmel AVR, or a microchip, or an STM32, or an Arduino, depending on what your college has decided to do. Either way, it'll be an introductory task where you start learning about microcontrollers, you start learning how to use GPIO, and you're programming bare metal in C. This is an easy S tier because microcontrollers are the absolute lifeblood of embedded. You should learn the basics of registers, timers, interrupts in this class. Absolutely not one to miss. On the other side of the spectrum, we have Coding 1, or Introduction to Programming. Now, if you've done any amount of programming or coding before you take this class, it literally feels like smurfing. It's just too easy, you don't learn anything, it's very basic, and it's done in high-level languages like Python and JavaScript. This one is going in the D tier, and the reasoning behind that should be obvious. If you're looking to be a firmware engineer, this stuff should be trivial for you. Okay, Digital Systems 1 is actually an interesting one to place. This is where you learn about things like binary representation, logic gates, truth tables, flip-flops, multiplexers, things like that. And you look at like ALU slices and CPU architecture a little bit as well. This one is a very solid class. It's quite foundational though. And to be honest, if you're writing programs in C, you don't really use a lot of the logic gate stuff that much. You do get to use it if you ever look into doing things with op-amps or integrated circuits. So this one, for foundational knowledge, it's really good and everybody should take it. But in terms of like applicability to day-to-day, I'm going to put this one in the B tier. Circuits 1, guys, get excited. We're going to blink an LED on the breadboard. It's going to be great. We're going to learn about Ohm's law. We're going to learn about Kirchhoff's current laws, how to do circuit analysis, a little bit of op-amp stuff. Now look, this is a very foundational course. It is core. You need to know this stuff. But in terms of bang for buck, honestly, you could get a book online and learn this level of content. It's not necessarily something that you need to do in college. And for that reason, it's going with Digital Systems 1 in the B tier. Very core, very foundational, but in terms of bang for your buck, when you're learning this stuff, it's a B tier. Digital Systems 2 is an awesome class and definitely not one to miss. This is where you learn about FPGA design, ASICs, pipelining, hardware acceleration, all of that good stuff. So another thing to consider is that FPGA boards are notoriously expensive, so if you can get access to this hardware through your college, this is an awesome way to do that. And FPGA design seems to be one of the most gate-kept secrets in the industry. There are very few resources that are good out there for it. You'll learn about things like VHDL and Verilog, which is how you actually do hardware markup in like a text-based interface. Kind of like code, but not really. This is definitely not one to miss because you'll finally get to understand what people say when they say, oh, this thing is hardware accelerated, because you literally write a hardware accelerator in this course, often for digital signals processing or something like that. It's going in the A tier purely because FPGA roles are sparse compared to the rest of the embedded world. It's kind of like a little subset of the embedded world in terms of jobs. There are definitely jobs out there for talented FPGA engineers, but it's definitely a niche down for you to get into. Up next, we have a spicy one, Operating Systems Architecture. This is a really cool class. You'll dive underneath the hood of one of the big major open source operating systems like Linux or BSD. It's usually done in C. You'll learn how drivers work. You might even write a driver. You'll learn how things like PCI work. You'll learn how the kernel handles interrupts, DMA, things of that nature. Now, this is a very cool class. You also get to learn about things like CPU scheduling and memory management and multi-core processing. It's also quite a difficult class. And to be honest, if you're looking to be an embedded engineer, this stuff really applies for higher level operating systems. So this is useful if you want to do something like embedded Linux, but if you're going to be doing more traditional things like microcontrollers and even RTOS, this is a little bit more complicated than you might be expecting. So for that reason, I'm going to put it in the B tier. Very cool, very interesting, also very difficult, and maybe a little bit overkill. Coming up with another hard but very valuable course is Control Systems. This stuff is not easy. In fact, it's one of the more difficult courses that I took when I was doing my university program, but it was also one of the most valuable. There are so many control applications in embedded that you'll be doing things like PID for. So think, for example, like electric motor control, or controlling the temperature in a room with a thermostat. This stuff is everywhere, especially in manufacturing. If you want to build embedded devices for manufacturing or in vehicles, you need to know control systems. It is difficult, it is valuable, PIDs are everywhere in embedded, it's going in the A tier. The only thing that stops it from being in the S tier is that not all applications of embedded use control systems. For example, a lot of Internet of Things device don't really bother with that. And so while it's a good class just to know about, you may not always be using this stuff. And it's done in MATLAB too. Like, MATLAB sucks, I hate it. Now, you may think that the embedded world is all digital. We're living in a digital world, baby. It's all zeros and ones. But actually, when it comes to interfacing with the real world, we often speak in analog quantities. So for example, I just mentioned you could do temperature control in a thermostat if you learn how to do control systems. But how do you actually read that temperature in from the real world? Well, you'd be using like a thermistor or something like that. And for that, you need to know about analog signals. Note, this is not what the A in AC stands for. Analog and alternating current are two completely different concepts, so don't get them confused, even though they both start with A. Analog signals simply refers to a voltage that falls within a range instead of being a distinct high or low value. And as embedded engineers, we need to know how to interface with analog signals in order to read and operate in real-world quantities. So what do you learn about in analog signals? You learn about things like analog to digital converters, you learn about resolution of ADCs, quantization, you'll learn about the Fourier transform, you'll do filter design and digital signals processing. These are all incredibly useful applications that are very widely applicable in a lot of embedded devices, and it's simply going in the A tier. The only thing stopping it from going in the S tier is that a lot of the maths that you learn in this, you won't use in a lot of cookie cutter generic embedded applications. So the Fourier transforms that I mentioned before, you may not be using them day to day on the job because things are often very highly abstracted from you. Microcontrollers too, come on guys, this is an easy S tier. This is a more advanced embedded class where you learn about things like wireless, Bluetooth Low Energy, MQTT, you'll learn about RTOS like Zephyr and FreeRTOS, you might use a full RGB color graphic display, and be expected to do multi-MCU communication in order to make important things happen. This is really cool stuff. It's very close to what you'd be doing in a lot of real-world applications. There are a lot of Zephyr roles out there, there are a lot of RTOS required roles out there. Learning the NRF stack is very important as well, because up to this point, at least at my uni, we didn't touch NRF stuff. We only used like ST or Atmel stuff. And I said before that the reason operating systems architecture is in the B tier is because learning about those operating systems is a bit overkill and it's a lot to take in. Well, fortunately enough, at least with FreeRTOS, Zephyr's a bit complicated, but FreeRTOS is simple enough that you can kind of understand exactly how it all works, and it's much easier to digest. You can kind of learn how the scheduler works, you can learn about the different heaps and how the heaps work and how they handle fragmentation and stuff like that. It's much more simple and much more grounded because the microcontrollers that it has to run on are so much less powerful than what, say, Linux gets to run on. And so it has to be more simple by design, and it's kind of easier to learn the base concepts of operating systems and understand them. So the stuff that you learn about in operating systems architecture, you also kind of learn about that in real-time operating systems, but it's much more simple and easy to understand in this context, and also directly relevant to embedded roles. If you have any opportunity to do an embedded project course, please, for the love of God, take it. This was the single most valuable, and in fact, I'm going to put this at the front here. This was the single most valuable course that I took in my entire degree at uni, and I was actually a teaching assistant for this particular course. The project course is where you go from start to finish, build and design and program an embedded device, do the PCB, do the firmware, do the schematics, do everything from scratch. It is absolute gold. It is the closest that you will get in university to a real world project. It is an absolute must take. If I could be bothered, I would add an S+ tier and put it in there. This project course is just in a league of its own, especially if it's in a team. I know a lot of people hate team projects, but at the end of the day, your real work is going to be done in a team. And so if you're looking for the most valuable and the thing that is going to get you the closest to industry, it is the one. And I'm not just shilling this because I used to TA for it. Genuinely the most valuable in the entire degree. The only other thing I might say to that as an addendum is that to do the project course, you actually need to have taken a lot of the more fundamental stuff. You can't just dive right in, otherwise you're going to be dead weight to your team. So this other foundational stuff that we've talked about is important, but at the end of the day, after you've learned that and you get to do the project, it just clears everything. Low-key, I think I'm going to get a bit of hate for this, but I'm going to put electromagnetic waves in the C tier, because unless you're doing something with antennas, radio frequency, or high-frequency PCB traces, this kind of stuff is really freaking hard. It's actually so hard, and there's not that much upside to it if you're just doing any kind of regular digital systems design kind of stuff. In this class, you'll learn about transmission lines, which is kind of the theory underlying high-speed PCB designs. You'll learn about antennas, radio frequency, impedance matching. It is also home to the infamous Smith chart, which is probably one of the most triggering things you could show any electrical engineering student or graduate out there. Take at your own peril. That being said, while it was really hard, I found it really interesting. I was just not that good at, which probably skews my opinion on it a little bit. But that being said, it's really important if you want to do electric motor control, radio frequency stuff, anything of that nature. I just don't think the value proposition is there regarding how hard it is versus something like operating systems architecture or control systems. Transistors, the fundamental underlying component in all modern semiconductors. Hate me all you want, this is going in the B tier, okay? It's a cool class, you get to understand a little bit about how transistors work under the hood, but at the end of the day, in most cases in your day-to-day embedded world, unless you're going into like silicon design, you're going to be using them as a glorified switch. So at the end of the day, all the complicated stuff that you learn about in here, some of it is applicable, like you've got to know what region all of the transistors are operating in when you do your design based on what electrical circumstances are going on. But in terms of knowing how the chemistry underlying them works, yeah, unless you're doing like silicon design, it's not really going to be a huge thing for you. So that's why this is in the B tier. Now this rating might improve to an A tier if you're doing anything like electronic speed controllers, or if you're doing power electronics in any sense of the word, because then you really, really have to know about transistors, how they work, all the operating conditions of them, otherwise you're gonna blow stuff up. But at the end of the day, if you're doing more basic embedded design where they're just switches, then this would be in the B tier. Now, computer networks are really near and dear to my heart. In fact, in my current role as a software engineer, I know, crucify me, I'm doing high-speed computer networks. Now, at the end of the day, if you're doing embedded roles, networking, you have to know about like TCP IP, and that's kind of about it. You don't really have to know about how the internet is structured. You don't have to know about BGP. You don't have to know about routing too much. You don't have to really deal with that unless you're writing like Wi-Fi drivers. At the end of the day, you really just have to know how to connect it to the cloud in order to do your Internet of Things thing. And so the more complex parts of computer networking like firewalls, don't apply in this case, and that's why I'm putting it in the C tier. Networking is still important if you're doing stuff on embedded Linux or with Zephyr, but at the end of the day, you don't have to know how the internet works, you just have to know how to give your thing an IP address and chuck some data over MQTT. Now finally, to finish off the video, we have AC circuits, alternating current circuits. This is things like transformers, a lot of power transmission is done with AC, and you've got things like some AC motor designs. I'm putting this in the D tier, dude. I'm sorry. I'm gonna get hate for that. Low key though, when you do embedded, you kind of just assume a digital domain unless you're doing like AC motors. At the end of the day, that's kind of what it is. You know, you get power in over USB, that's DC. You get power in from one of those little like power jack ports. Well, it's got a DC box when you convert it to the power outlet. AC, it's tough. It's like very situational. The transformers stuff is more applicable to like power substations. If you don't want to do like serious, like big power, if you don't want to go work at, I don't know, the Australian one is like Energex or something like that. I don't know, man. It's just not that good for embedded. Like, still take the class and still learn about AC, but it's just not that important in my opinion. And that's the final tier list. Now, I know that I'm going to get hate for this because everybody likes what they like. Everybody, like some guy is going to be super into EM waves and is going to be mad that I didn't put it in S tier. You know, some person is going to hate RTOS and say you should put that in D tier. RTOS, like I hate it, it's too abstract, etc., etc. But at the end of the day, I think this is fair. But please tell me in the comments if you would do this differently. I'd really love to talk about it. Thanks, guys.